Okay, so molar mass. We often need to essentially count atoms. We want to know how many atoms there are, but there's way too many of them to count. So we use the same approach that we use for things like shrimp or nails at the hardware store. We count them by weighing them. And so we're going to learn something about buying shrimp today. So shrimp are normally sold by the count, which is how many shrimp are in 1 pound. So if you have really big shrimp, there's only going to be a few in 1 pound. And the little tiny ones, there's going to be a whole bunch in a pound, right? So if you have a 41 to 50 count, you'll say that on the package, that means that you're going to have, in this range, between 41 and 50 shrimp per pound. They're not going to tell you exactly because not all the shrimp are the same size, so they're giving you this little range. Smaller count, larger shrimp. The really big shrimp, the tiger prawns, might be 10 to 15 per pound. So we can count shrimp by weighing them. So let's say you're having a party and you want to have 200 shrimp because maybe you've got 50 people and you'd like for everybody to be able to have 4 shrimp, right? So how many pounds of shrimp do you buy? Well, that depends on what kind of shrimp you're buying. If you looked at 2 pounds of the 41 to 50, there's 41 to 50 in each pound. If I have 2 pounds, then I have 82 to 100 shrimp. So if I want 200 shrimp, I would need at least 4 pounds. 4 pounds would give me at most 200. So if I wanted to make sure I had 200, I should probably buy some extra. Any questions about the idea of counting shrimp by weighing them? Okay. We do a very similar thing with atoms. It's just a lot more precise. We're not going to have big ranges like that. We're going to have more precise numbers. We often in chemistry need to know how many atoms are in a sample. And that's because when we look at a chemical reaction, it's happening between individual particles. If I have 1 of these, I might need 1 of those to make 1 of that. Or I might need 1 and 3 to make 2 of that or something. And so we're interested in the number because that's how the atoms react. So 2 hydrogen atoms and 1 oxygen atom form 1 molecule. So we count shrimp by weighing them. A lot of things, other consumer items are also counted by weighing them. You buy a bottle of ibuprofen tablets. It says there's 100 tablets. Now, most people don't actually empty it out and count all of them. I had to do that once because my 2-year-old opened the brand new bottle of Tylenol and had been playing with it in the kitchen. They were all over the floor. And he was sick, and I had already given him children's Tylenol. So Tylenol's toxic if you get too much of it. So I really needed to know if he had taken too many or not. So I gathered up all the pills and I counted them. 104. It's like, so the company knows that people get mad if there's not the right number in there. People don't get mad if there's a couple extra. They don't count all those pills. They know how many how much 100 ibuprofen tablets should weigh. And so they put them in the jar until it weighs that, and they send them on. So sometimes you get a little more, right? So, yeah, we ended up having to go to the emergency room and have a blood test done, and turns out he hadn't eaten any of them. But so much fun, right? Children. Other things, we use these counting units like a dozen. We all know what a dozen means, right? A dozen means 12. 12 what? 12 whatever you have a dozen of. It could be a dozen eggs, which now costs like week's wages or something. So expensive, but a dozen eggs is 12 eggs. A dozen donuts is 12 donuts, right? Another unit like that is a gross. Gross, right? A gross is a dozen. So if you have a gross of something, you have 144 objects. You're more likely to encounter a unit like that if you work in a warehouse or something. Another counting unit is the ream, a ream of paper. You know what that means? 500. A ream of paper is 500 sheets of paper. Some of them weigh more than others because they're higher quality paper, but when you buy a ream, it's 500 sheets. So instead of dozen or ream or gross, we have our own unit, and it's called mole. So M-O-L-E, mole. And we often refer to this as the chemist's dozen. So a mole is however much stuff has 6.02214 times 10 to the 23rd particles in it. Those could be atoms, they could be ions, they could be molecules. So 1 mole is equal to 6.02214 times 10 to the 23rd particles, just like 1 dozen is equal to 12 things. It's just a bit bigger. That number has a name. It's called Avogadro's number, named after Avogadro, who did the work that led to figuring out what that number was. So 1 mole of anything is Avogadro's number of the thing. So you could have Avogadro's number. You could have a mole of eggs. They're not going to fit in your pickup. They're not going to fit in the Costco. But you could. The mole is a great unit because if you have a mole of a substance, an ion, not really an ion, but an element or a compound, it's a reasonable amount of stuff. It's enough that you could see it with your eyes, but you could also probably hold it with your hands. So an example here, 22 solid copper pennies have approximately 1 mole, 6.022 times 10 to the 23rd copper atoms in them. A tablespoon of water is approximately 1 mole of water. Any questions? Well, where did that number come from, Avogadro's number? Well, it came from the definition of the atomic mass unit, in a way. So the value of the mole is equal to the number of atoms in exactly 12 grams of pure carbon-12. Remember we said the atomic mass unit was 1/12 the mass of a carbon-12 atom. So 12 grams of carbon is equal to 1 mole of carbon atoms. 1 mole is always 6.022 times 10 to the 23rd things. So we usually leave off the 1/4 because 4 sig figs is good enough. So that's a good number to memorize because it comes up a lot. So this gives us a relationship between the mass of something and the number of atoms in it, and allows us to count the atoms by weighing them. We can use dimensional analysis to convert between moles and number of atoms, and it's done in the same way that we would convert between dozens and numbers of eggs. Excuse me. So we know that a dozen eggs is 12 eggs. So they don't have it right now because of the egg shortage. But normally, Costco sells, I'm not bitter about that at all. Normally, Costco sells a package of 5 dozen eggs. Well, how many eggs is that? 60. See, we can do that in our heads because eggs and dozens make sense to us, right? But we get to moles and atoms and we're like, oh. It's hard to think about. And then there's that crazy number. Well, let's look at how we would do that with dimensional analysis using a dozen. So if we're trying to find out how many eggs, we want eggs to be in the numerator because that's the unit we want to keep. We're going from dozen to eggs. Let's put the path up here. We're going from dozen to number of eggs. So that's my path, one arrow, one conversion factor, dozen to eggs. And then I'm going to put dozen down here so that that unit cancels out. And then I ask myself, well, what's the relationship between number of eggs and dozen? There's 12 eggs in 1 dozen. And then you end up with 60 eggs. Okay? Do the same thing using the chemist's dozen with Avogadro's number instead of 12. So 1 mole is equal to 6.022 times 10 to the 23rd atoms. So we can make a conversion factor like that using this relationship. Sometimes students put the number with the wrong thing, and they'll say that there's 6.022 times 10 to the 23rd moles in 1 atom, which is like telling me that 1 egg is equal to 12 dozen eggs. No. So, if you are mixing those up, put in the word dozen for mole, because it's the chemist's dozen, and make sure that what you're writing out makes sense. So here's a question. A pure silver ring contains 2.80 times 10 to the 22 silver atoms. How many moles of silver atoms does it contain? Read the question. Here's a number. And then I'm going to ask myself, well, what is it asking me to find? How many moles of silver? Dang it. How many moles of silver? So I'm given 2.80 times 10 to the 22 atoms. And I'm trying to find moles. So then I'm going to figure out, well, how can I get from atoms to moles? Well, we just learned that relationship between moles and number of atoms, right? So we can go directly from one to the other. So 2.80 times 10 to the 22 atoms. I've got one arrow, so 1 fraction. Atoms to moles, atoms to moles. Mole is a very short word. It's only 4 letters, and yet it has an abbreviation, MOL. Right? And then we end up using the word molecule, which is really long. There's no abbreviation for molecule. They didn't ask me about that, but it is what it is. So MOL or MOLE, same thing. And so I want atoms down here, so the atoms cancel out. And so then I know Avogadro's number goes in here somewhere, but mole is dozen and atoms are eggs. So I want Avogadro's number to be with the eggs, or the atoms. And it's really long, and so I usually don't leave enough space for it. Now, you definitely want to do this one on your calculator. If you're using scientific notation, maybe not wrong, but in an alternate way on your calculator, you might get this one wrong. And that's going to let you know that there's a better way to do it. So remember, we want to use our EE button or our EXP button. So I'm going to do 2.80 EE 22. Divide 6.022 EE 23 equals. And I can look at the numbers I'm starting with, 3 sig figs and 4 sig figs. That tells me my answer is going to have 3 sig figs. So that's where the last sig fig is. I'm going to write down 2 more. And then I can round that to 0.0465 moles.
Mind if I use the yellow chair? These
No,
stools
not
are
at all.
very uncomfortable for long legs.
They are very uncomfortable. Feel free. So if you're using scientific notation incorrectly, you're going to still get the 465 part, but it's going to be something like times 10 to the 44. Anybody need me to talk to their calculator? Good. So here the number was written in scientific notation. I did not write it in scientific notation here. When should you write it in scientific notation? Well, sometimes you're like, it's an exam or mastering chemistry, and it tells you to use scientific notation. Sometimes it's multiple choice, and the answers are in scientific notation, so then we have to use scientific notation. Other times we could go either way. My personal rule of thumb is if there's more than 3 zeros at the beginning or the end, I'm going to go for scientific notation. This only has 1 0 at the beginning, so it's fine as decimal, but scientific notation is always okay. So we need one more thing to convert mass to number, and that is the mass of 1 mole of atoms. And this is where the relationship with the atomic mass unit comes in. An element's molar mass in grams per mole is numerically equal to the element's atomic mass in atomic mass units. The mass of 1 atom in atomic mass units is the same number as the mass of 1 mole of atoms in grams. It's not a coincidence they set it up that way, so things would be easier. So aluminum, 26.98 grams of aluminum is equal to 1 mole. 1 mole of aluminum is Avogadro's number of atoms. 12.01 grams of carbon is 1 mole of carbon. How do we know that? We find carbon on the periodic table, and the number underneath says 12.01. That's the mass in grams of 1 mole, or the mass in atomic mass units of 1 atom. And just like with the shrimp, that's not a good correlation with the shrimp. Never mind. So we call that the molar mass. It's the mass of a mole, as opposed to the atomic mass, which is the mass of an atom. So 12.01 grams of carbon is equal to 1 mole of carbon, and so we can make 2 different conversion factors to use in dimensional analysis. Calculate the amount of copper in moles in a 35.8 gram pure copper sheet. So we're given 35.8 grams, and they're asking for amount of copper in moles. Take the numbers out of the equation, write them down with their units. So I've got that many grams of copper, and it's asking me to find the number of moles. So I'm trying to find moles. We can do this in one step using the molar mass of copper. So if we find copper on the periodic table, it's a symbol copper, and this one says 63.546, and it's element number 29. This number tells me the mass of 1 mole of copper. So 35.8 grams, 1 arrow, 1 fraction. This is the path, grams to moles. So that's going to go on the top of all of my fractions, grams to moles. And then I need this unit to go away, so I'm going to divide by that unit so they cancel out. However many steps I have, I'm going to get all my units in there, and then I'm going to stick the numbers in, because the units tell me where to put the numbers and I don't have to think about it. So from this information on the periodic table, I know that 63.546 grams for copper is equal to 1 mole. So 1 mole is 63.546 grams. As is often the case, the number that I'm starting with has 3 sig figs. My molar mass here, this periodic table showed me 5 sig figs. The one I give you on an exam shows 4 sig figs. So you can use more, it's never going to hurt anything. But don't round this number down to less than 4 significant figures. Because especially this one, 63.546, that would round up to 64, but it isn't 64. It's almost in between 63 and 64. So we don't want to round our molar masses. So this should have 3 sig figs, and so I'm going to report my answer as 0.563 moles of copper. Any questions? This gram to mole thing is something that comes up throughout the rest of the semester.
Which I hate.
Oh, I'm sorry.
I thought that was bad. It's just repetitive.
Yeah, it is. We could ask stoichiometry how it feels about you.
It feels nothing. It's like geometry. But I mean,
Okay.
like, later in the semester, we have to use
So now this is the plan that we're going to use to count atoms by weighing them. If we have the mass, we can calculate how many moles there are, and that's using the molar mass of the element. It's on the periodic table. Once we have the moles of the element, we can find out how many atoms there are using Avogadro's numbers. So how many carbon atoms are there in a 1.3 carat diamond? Diamonds are a form of pure carbon. 1 carat is equal to 0.20 grams. Read the question, pull out the numbers, and find what it's asking for. How many carbon atoms? So I'm going to write down the numbers I was given. 1.3 carats, nothing to do with the vegetable. And I'm told that 1 carat is equal to 0.20 grams. We're going to do this with dimensional analysis, but we're starting out with more than one number, and so sometimes it's hard to know which one do I start with. Well, this is a relationship between 2 units. We could express that as 0.20 grams per carat. Per. This is going to be a conversion factor. This is just a carat, a mass of a diamond. It can't be used as a conversion factor. So this is what we're starting with. And we're trying to end up with carbon atoms. And we have to figure out how to get from carats to carbon atoms.
Carat to gram, gram
Yeah, we can do carat to grams because they gave us that relationship. We don't expect you to remember how many grams are in a carat. I don't remember. So we could go from carats to grams using the relationship they gave us. And then how do we get from grams to number of atoms?
Grams to moles.
Grams to moles. And from moles we can go to atoms. So here we had a unit in the middle that was missing, right? So a lot of times in chemistry, there's moles somewhere in the middle. Moles in the middle. Remember that TV show Malcolm in the Middle? Yeah, there's moles in the middle. Okay. So that's our path. Carats to grams to moles to carbon atoms. So I start out with the number I was given, 1.3 carats. I look at my path, I see it has 3 arrows. So I'm going to write 3 conversion factors. You could do this in fewer by looking stuff up, but that defeats the purpose of the problem. And once you get the hang of dimensional analysis, it's probably going to take you longer to look up the relationship between carats and carbon atoms than it is to just sit down and do it. So carats to grams to moles to atoms. It's just what I've written here. Carats to grams to moles to carbon atoms. The first unit becomes the denominator for the second term because I need that unit to cancel out and go away. Now I need grams to go away, so the next term I'm going to divide by grams. Now I need moles to go away, and so I'm going to divide by moles. You see the pattern in there? Once we get this path, it always just falls into the same pattern. Okay? There are things that we have to think about and puzzle out. But let's save our brain power for where it's needed, and let's find more automatic ways to do problems like this. So the key to this is this part right here. Okay, now I need to put the numbers in. I'm going to start with this one because it's right here. So 0.2 is with gram, 1 is with carat. I have to keep them in their places. So 0.20 grams is equal to 1 carat because the top has to equal what's on the bottom. What's the relationship between moles and grams for carbon?
1 mole is 12.011 grams.
Yeah, so we look at the periodic table and it says 12.011 grams. That one says 12.0108. Would round to this. That's more than 4 sig figs. And here we have the atoms and moles again. Atoms are like eggs, moles are like dozen. A dozen is 12 eggs. A mole is that funny number of atoms. So this is what my calculator is showing me. Occasionally, a student will write down, like, there's 1.304 atoms in there. Because they just looked at the beginning of the number. The beginning of the number is always important, right? But they overlooked the very end here. This E22 means times 10 to the 22nd power. Really, really big deal. Right? So always look at your whole number and make sure that you're not leaving something off.
Yeah, it just got mirrored, so.
So this would be 1.3 carats, and so I'd have 2 sig figs here. I'm going to get 1.3 times 10 to the 22 atoms. Any questions?
I think I got something, either I got something wrong or you got something wrong here.
What are you
Got
getting?
that. What did I do?
equals? Mercury?
I mean, that looks right.
So how big is Avogadro's number?
I don't know how I messed that up.
It's very easy to do. My husband calls that a brain fart. Right? I don't know why my brain did that, but it did. So if we had a mole of pennies, Avogadro's number of pennies, it would cover the entire surface of the Earth to a depth of 300 meters. This is a meter stick. It's always a meter stick. 300 of these tall. The whole Earth, oceans included, 300 feet tall in pennies. That's a lot of pennies. It's mind-boggling.
I think there's more, there's not like enough grains of sand in the earth to amount to that.
No, there aren't. So if we had Avogadro's number of grains of sand, it would cover the state of Texas to several feet. If you counted for 24 hours a day, no potty breaks, no rest breaks at all, no checking your phone, counted for 24 hours a day, rest of your life, you couldn't get to Avogadro's number.
I think to put it into perspective, it took one man 88 hours straight to count to 1 million.
That seems reasonable. So here, if we write it in decimal notation, let's see, this is 1,000, million, billion, billion, trillion, quadrillion, quintillion, sextillion. So 602 sextillion, 200 quintillion things. I mean, compared to that, the national debt is nothing. Absolutely nothing. Okay, so let's put some things together here. So this is a critical thinking problem. It's taking things that we have learned or should know how to do, but putting them together in a way that you haven't seen before. So this is a titanium cube, contains 2.86 times 10 to the 23rd atoms. What is the edge length of the cube? The density of titanium is 4.50 grams per cubic centimeter. So you read the whole thing, and then you pull out the numbers. So there's a number, here's a number. I'll write those guys down. 2.86, that's supposed to be a 6, times 10 to the 23rd atoms of titanium. That's Ti. And we have 4.50 grams. That's grams per cubic centimeter. Let's write that as a vertical fraction so we can really clearly see that it's a fraction. What are we trying to find?
The edge length, that means we're trying to get just centimeters.
Right. Yeah, so the edge length, that's probably going to be in centimeters. Okay, so let's draw a little picture. So if we have a cube, let's call the edge length L. That's what they often call it. So that's L, and this is L. And the volume of that cube is L times L times L, or L cubed. So if we knew the volume, we could calculate L using this equation, right? So let's try to find the volume of this. Well, we've got two things here. We've got number of atoms and we've got grams per cubic centimeter. This is a conversion factor. So we're going to start with atoms. And if I'm going to try to get to volume, a convenient unit for volume here might be cubic centimeters. And I'm getting that from this guy right down here. If this was cubic kilometers, then I'd use cubic kilometers probably. So then we have to figure out, how do we get from atoms to cubic centimeters? We haven't done that. Well, let's think about it. So this is grams in cubic centimeters. We start at the end and say, well, if I had grams, I could get to cubic centimeters using the density. So now I'm going atoms to grams. Oh, that sounds a little bit familiar. I think we did one of those, right? What's the missing unit in the middle? Moles. So let's put moles in there and make sure that's going to work. Atoms to moles, Avogadro's number. Moles to grams, atomic mass, molar mass on the periodic table. Any questions about how to get the path? That's really the hardest part. Okay, so now that I have that, I can go ahead and calculate the volume. 2.86 times 10 to the 23rd atoms. There's 3 fractions. The units are atoms to moles to grams to cubic centimeters. So the first unit becomes the denominator in the second term, because those will cancel out. And moles comes down here, and grams comes down there. There are other ways you can solve this, but this technique is going to work great when we get to stoichiometry. So it's worth learning, even if you choose not to use it later. Now we need to put numbers in. Well, this guy, 4.5 grams, is equal to a cubic centimeter. That's going to go over here where I have cubic centimeters and grams. The 4.50 was with grams. It needs to stay with grams. Moles and atoms, that's like dozens and eggs, right? Except instead of 12 eggs, it's Avogadro's number of atoms. So 1 mole, and again, I didn't leave enough room. It's a very common problem for me. There's Avogadro's number. Grams per mole, we just need the periodic table. We need to find titanium, being careful not to confuse it with thallium, which is TL, 47.867. Grams is 1 mole. So I figured out a path for the units. I made that into an equation. The units in the equation show me where to put the numbers. Isn't that beautiful? This is so much less thinking. No rearranging of the density equation. There's really no algebra in here. There's just plugging things into your calculator. So 2.866, no, 2.86, AE23. As you put this into your calculator, you don't need parentheses, and you can just go straight across. Times 1, divide by this, times this, divide by this, times this, divide by this. If you want to skip the ones, you can just leave them out, right? So I think times 1, but I'm dividing by 6.022 EE23 times 47.867. Divide by 1, multiply by 1 if you like, divide by 4.50. So that is equal to, and this is all multiplication. I've got 3 sig figs. Is the smallest, so I'm going to have 3 sig figs here. 5.05. And I'm going to write down the next 2 digits, and the units there, cubic centimeters. Okay? I don't want to round it off yet because I'm not done. But I can save myself some thinking later by just making a little note to myself. That's where it would end if I was going to round it. So now we can take this guy over here. The volume is equal to the edge length cubed. Well, this is my volume, right? I'm gonna put it in a different color because they're getting kind of confusing. So 5.0518 cubic centimeters is equal to L cubed. How do I undo L to the third power and just get L?
Cube root.
Cube root, right? The square root undoes a square, the cube root undoes cube. So I'm going to take the cube root of this and the cube root of that. So the cube root of L cubed is L. The cube root of centimeters cubed is centimeters. Now, how you do this on your calculator depends on your calculator. So for the TI-36X Pro, I'm going to press 3, and then there's a button that looks like this. Press that button. I put in the root I wanted first, 3, and I press that button, and then I type in the number 5.0518, and
Sometimes
press
it's a little
equals.
X instead of a square.
Yeah, there's different ones. And so this ends up being equal to 1.7158. Just writing the next two digits down, centimeters, and so that would be 1.72 centimeters.
I think on my other super fancy one, it shows it as with an exponent of negative something. That's another way to do it if you can't find it.
Yeah, so if you don't have that button,
No, it's multiplying a fraction.
Yeah.
Or fractional exponent.
So I have a button also that's X to the box. You can use that. Or you could use that caret button.
Do a fractional exponent.
Right. So the cube root is raising it to the 1/3 power. So 5.0518 to the 1/3 power is going to give me the same answer. We're not going to do cube roots very much, but they show up a little bit. Any questions?